Hello everyone. Today's question is HSC Mathematics 2019 question 16 part A. A person wins $1 million in a competition and decides to invest this money in an account that earns interest at 6% per annum compounded quarterly. The person decides to withdraw $80,000 from this account at the end of every fourth quarter. Let AN be the amount remaining in the account after the nth withdrawal. Part I, show that the amount remaining in the account after the withdrawal at the end of 8th quarter is A2 is equal to 1 million times 1.015 to the 8 minus 80,000 times 1 plus 1.015 to the power of 4. And part 2, II, for how many years can the full amount of 80,000 be withdrawn? Just fix that at the end of 8th quarter. Alright, let the amount after first withdrawal be A1. So A1 is equal to our original amount which we have invested, $1 million, times by 1 plus 0.15. Okay, why 0.15? Because that was 0.0. Because 6% that is the interest per annum can be written as 0.06, but because it's compounded quarterly, you got to divide it by 4, and that gives us 0.015. So that is going to find the amount left after the first withdrawal. For this period, we should have a power of 4 because the number of quarters when the first withdrawal is done is 4. So the person waits for 4 quarters before making any withdrawal. So that is the money that person has at the end of the 4th quarter before making any withdrawals. So if that person makes 80,000 withdrawal, you got to take that away from him. Alright, that is the money left after first withdrawal. Okay, for the second withdrawal, for the amount left at the after the second withdrawal is made, we start with that much money. So that is how much left in the account. So I can write it as 1.015, 1 plus 0.15, to the 4 minus 80,000. So that's the amount we started with. And again, this has stayed for another 4 quarters. So we need to times by that to see how much this money that we started with grows to, minus another 80,000. That will give us A2 is equal to 1 million. If I expand that, that is 1.04, this is another 1.015 to the 4, that's another 1.015 to the 4. If I times them, it becomes 1.05 to the 8. Then if I expand that, that becomes 80,000 times 1.015 to the 4 minus 80,000. And if we factorize for 80,000, we get the expression that they are asked from. So okay, as required. That is for part I. For part II, for how many years can the full amount of 80,000 be withdrawn? When that happens, the balance in the account will be 0 or close to 0, or basically less than 80,000, because they want the amount to be full amount of 80,000. So if we look at the pattern that we had, if we work what is A3, A3 also will be end up with A2, so that's your starting value for A3. So you times A2 by 1.015 to the 4, and you take away 80,000. That's your starting point, starting value, and you wait for 4 periods, so this grows by that based on the compound interest formula. Then take away 80,000, which is the amount you withdraw. And again, if I work this out, A3 will be, I sub in for A2 from here, so I get 1 million times 1.015 to the 8 minus 80,000 times 1 plus 1.015 to the 4. Okay, that's A2 times by 1.015 to the 4 and minus 80,000. If we expand that, that becomes A3 is equal to 1 million times 1.1015 to the 12 minus 80,000 times 1 plus 1.015 to the 4 times 1.015 to the 4 minus 80,000. And if I factorize for 80,000, That gives me 1 million times 1.015 to the 12 minus 80,000. 1 plus 1.015 to the 4 plus 1.015 to the 8. Alright, now if we generalize this formula, we see that here we have A3 and here we have 12. So this is always 4 times that. If you look at here is 2, then you have 8. Then if you look at the brackets, which is times by 80,000, if this is 8, you have 4, then you start from 1 and you go all the way to the power of 4 for 1.015. In here we have a power of 12, and the maximum power that we reach for 1.015 is 8. So always 4 less than that. So having this in mind, AN will be equal to 1 million, so just generalizing this formula, times by 1.015, so 3, 4, and 2, 8, so 4 times n, minus 80,000 times 1 plus 1.015 to the 4, 1.015 to the 8, and all the way to 1.015 to the power of 4n minus 1. 4n minus 1. 4n minus 1. We've got 12 here, we've got 8 here. And we've got 8 here, we've got 4 there. So 4 less than this power. Okay, so that's where we end. Now we can add this up because it is a geometric series with your A equal to 1 first term, and your R common ratio is 1.015 to the power of 4. And for the number of terms, we start from, you can write this as 1.015 to the 0, then 1.015 to the 4, 1.015 to the 8, and all the way to 1.015 to the power of 4. I just factorized for n minus 1. So you got 0, you got 1 times 4, you got 2 times 4, and all that. Basically, you have all the numbers from 0 to 1, 2 to n minus 1. Okay? So all the numbers from 0 to n minus 1. So that means we have n terms. Okay, so the number of terms is n. Now using the formula for the sum of a geometric series, which is Sn is equal to A times r to the n minus 1 over r minus 1. So this, all the terms in the bracket add up to all of these terms, add up to A, which is 1, r, which is 1.015 to the 4, then to the power of n minus 1, divided by r, which is 1.015 to the 4 minus 1. Okay, so you got 1.015, these two times together is 4n minus 1 over 1.015 to the 4 minus 1. So this bracket is equal to this value. Now I sub in this expression, so I get an is equal to 1 million times 1.015 to the 4n minus 80,000 times by 1.015 to the 4n minus 1 over 1.015 to the 4 minus 1. Now we want to see, this is the amount left in the account after n's withdrawal. We want to see when this is going to be equal to 0. So letting it equal to 0, we will have 0 is equal to 1 million times 1.015 to the 4n minus 80,000 times 1.015 to the 4 minus 1, 1.015 to the 4n minus 1. Okay, our aim is to find 4n. Let 1.015 to the power of 4n be x. Let's call this x because it happens here and it happens here, and that's the only unknown we have. So that will give us 0 is equal to 1 million times x minus just x minus 80,000 times 1.015 to the 4 minus 1 x minus 1. Now multiplying both sides by this denominator becomes 0 is equal to 1 million times 1.015 to the 4 minus 1x minus 80,000 times x minus 1. And expanding and simplifying for x, factorizing for x, we get that times 1.014 to the 4x, and x is factorized minus 80,000. Alright, that is the value of x, and the constant ones which you are going to have, and we have also another x. So when you times that by that, you get that, and also you have 1 million. So 1 million. Now that then minus 80,000. That's all for x. And then you have minus 80,000 plus that becomes plus 80. Okay, from here we can find x, we can take it to the other side, and becomes x, if I take it to the other side, it comes minus 80,000 divided by the coefficient of x. So that becomes 1 million times 1.015 to the 4 minus, that is 180,000. Okay, both the top and bottom are negative, so it will give you a positive value for x. And if you sub that in your calculator, you should get 4.292. 4.29267. Alright, that is the value of x. But remember, x was x was 1.015 to the power of 4, which is now that much. So 4.29267 is equal to 1.015 to the power of 4n. Now, to find the 4n here, we can take, for example, ln from both sides. So ln of 4.29267 is equal to 4n times ln 1.015. So you know when you're taking ln, that goes up in the front, that the power goes there. So from here we can work out the value of 4n, and that gives us 4n is equal to ln 4.29267 divided by ln of 1.015. If you put that in your calculator, you should get 4n is equal to just sub that in my calculator again. ln 4.29267 divided by ln 1.015 equals, that gives us 97.853, and dividing this by 4, that gives us n. N becomes 24.46. Okay, so that is the number of withdrawals you can make from this account. So that many for quarters or that many years. So if you win that much of money and you invest it in an account that gives you 6% per annum interest, compounded quarterly, and you take $80,000 every year from your account, that account will last you for 24 full years. So you can make 24 full years withdrawal of $80,000. Thank you for watching.